Welcome to this lecture on the subject of microfluidic technology. I'm David Ball, the Chairman of the Power Industries Division Northwest Centre, and I'd like to thank you all for attending this lecture. It has been organised by the Power Industries Division Northwest Centre, and it is shared with the Greater Manchester area of the IMechE. The duration of the lecture will be about 40 minutes, followed with 15 minutes of questions. If you have any questions, will you please put them in the question box, and Fatima Shabata will field them after the lecture. Will you all please turn off your microphones and cameras during the lecture? Microfluidics is the study and application of fluid at small scales. Although these technologies have been applied mostly in health applications, energy applications present many opportunities that will be discussed in this lecture. The talk will highlight opportunities for microfluidics in electrocatalytic CO2 conversions, a means to lever renewable electricity to divert CO2 emissions and replace fossil sources for product and fuels. Our speaker today is David Sinton. He is a professor in the Department of Mechanical and Industrial Engineering at the University of Toronto. He is also the Canada Research Chair in Microfluidics and Energy. David is involved with developing fluid systems for applications in energy and analysis. The group is application-driven and is currently developing fluid systems to produce renewable fuels from CO2 and developing energy-efficient industrial working fluids. Ladies and gentlemen, your speaker for today, Professor David Sinton. Over to you, David.
Well, thanks so much, David, for the kind introduction. And maybe one question, David, before I get started. Am I right that most of the audience today is coming from industry, working in industry right now, or academia?
There will be some from industry, some from academia, and hopefully there will be some that have joined just because they're interested. I'm not sure how many.
Right, from elsewhere. Very good.
Yeah.
Oh, that's good. I got a sense for that. Thank you.
Yes, okay. I think there was about 70 to 80 people had registered to come. Great. And how many people are on, I'm not quite sure, but there's
all good. No, I just wanted to make sure I knew the audience, and yes, I think I've got it. Thank you.
But primarily, there will be mechanical engineers.
Great. Well, those are my favorite people as a mechanical engineer myself. And yeah, delighted to speak with you folks today, and hopefully you can see my screen there.
Yes.
Great. Okay. Yeah, so what motivates my work in energy has always been CO2 and global energy systems. And only one slide on the overall CO2 challenge here. The energy mix on the right-hand side, this has not changed too much over the last few years, but I should note a couple changes. This one, solar is up to 1.8%, I think now, and wind is over 2%. I teach a course at University of Toronto on the energy system, and I teach this like a clock. I divide the course and the lectures evenly based on our global energy usage by primary source. So that means that I do get to cover renewables, but of course it's fairly quick because they're a fairly small part of the energy system still. And then I cruise through the rest. And what I love about that approach is it's disciplined and it focuses on current energy systems. And it's a reminder, as I've taught that course over the last 10 years, that this chart doesn't change very quickly, and we'll talk about that. The overall challenge, of course, is CO2 emissions associated with the especially the fossil portions here, which are 85%. And then that challenge fundamentally large scale. That's something else that's important to note. This is an example. There's a few of these around the world, balloons that give you a sense of the size of 1 ton of CO2. And you can, you folks might know your carbon footprint, your personal carbon footprint for the year. For Canadians, it's about 15 tons. I think for you folks, it's a little less on average. So that's 15 tons of CO2 per year. So that's 15 big balls about this size at atmospheric pressure. So the humbling part for me is that this is a very large scale challenge. And of course, my expertise, as David nicely described there, is small scale stuff, right? So microfluidics is really this, so it's fluid mechanics and plumbing at small scales. Generally, we think around 100 microns, and I'll talk a little bit about scales around 100 nanometers today as well. So that's very small plumbing. So one thing I want you to come away with today is an appreciation for how these small scale tools can, if we're careful and thoughtful, can influence these large scale energy systems, right? These giant balls of CO2. And I'll give you some examples, and I'll also try to give you some examples of where in my career it hasn't worked. We've tried to have an impact in the energy system, but our small scale tools were not well suited to it. I'm going to cover 2 broad areas where we have had impact. The first is serving current energy operations. So here, CO2 operations, oil operations, gas operations, conventional energy stuff. How can microfluidics and nanofluidics help those? And I'll talk about how that was spun out into a company and how they offer those services worldwide. And then I'll talk about how we've applied that same tool set for renewable energy and specifically geothermal energy and CO2 sequestration, so CO2 removal. And then lastly, I'll talk about our most recent work, which is over the last 4 years or so, and that's using micro and nanoscale transport for CO2 conversion. And here, you'll note I was a little careful. I didn't say microfluidics here. I said microscale transport, and that's because these systems are fundamentally large scale. So what's the difference? The stuff I'm going to tell you about first is where information is the product, right? So you've got some fluids, maybe some CO2, maybe some oil, maybe some gas, and you want to get some data from that. You want to understand whether they're miscible or what conditions one might wet a reservoir. Information is the product. Small cell systems, microfluidics works great. What about when fluids are the product, when you actually want to convert CO2 at a large scale? Should you use a system that looks like this? No, you have to use something bigger. And that doesn't mean you can't use clever microscale transport, but it just means the system's going to look different. So you'll see those 2 different types, and it's really driven by the application. Is data the product? Information? Great. Type 1 is good. Is bulk fluid being produced, converted? Type 2. All right. So in type 1, the history of analysis in the oil and gas sector was traditional corp and sand packs. And we've largely converted this to what we call lab on chip technologies or microfluidic technologies. So in here, you might have imagined a chunk of rock that Schlumberger was doing services on and assessing. And we are doing the same thing, but with a glass chip. And we can see what's happening inside the pores. In this case, this is a solvent, and it's washing away some very heavy Canadian oil. And then traditional PVT cells. Here we've got a measurement approach for getting I believe it's minimum miscibility pressure. And we're doing that now in very, very small chips, and I'll show you those. So here again, in both cases, chapter 1, data is the product, information is the product, so microfluidics makes a lot of sense. our very first work in this area was looking at, mutual diffusion coefficients. So one fluid into the other. So mechanical and chemical engineers in the audience will recognize this. You've got a very heavy phase here and a solvent, right? And then over time, these two mix. And from those profiles, you can get the diffusion coefficients. And the great thing with this is very simple. The nice thing with this is you can get the diffusion coefficient in 100 seconds. Whereas if you were to use a conventional system like these things, you're looking at a day or something along those lines. A lot of testing, very intensive, very challenging. So these systems are fundamentally simpler when you're trying to measure transport properties, especially mutual transport properties like diffusion coefficient. I love this project because it really takes us back to our mechanical engineering undergraduate career. Hopefully, many of you have textbooks in your storage or in your basement, or maybe even on your shelf that have a phase diagram like this on there. Excuse me, feeling a little under the weather today, so hopefully you can hear me okay. So we've all got a textbook, hopefully, unless we sold our textbooks, which you should never do. And it's got the phase diagram for water, and you've got gas phase, and then you increase the pressure. You've got the liquid phase, and then increase the temperature. You go back over to gas, and I realized that we talk a lot about how we can control using microfluidics pressure and temperature. So I put it to my research group, hey, why can't we have a plot? Why can't we plot a chip that actually gives us the phase diagram? So this was an idea. We'd have an inlet, everyone with, pipe flows from coming in and out, and it's a high, small channel. You're gonna have a pressure drop, right? So P high to P low, that's pressure drop like this. And then temperature, we can stick something hot on this side of the device and something cold here, and we can get a temperature gradient. Now, this particular version didn't work. And I won't take you through all the scenarios, but the version that did work was this. We used a separator fluid, and you can think of this like a piston. And we were able to map the full phase diagram of two fluids. So this is an example of 1,000 little chambers at different pressures. So pressure left to right increasing, and temperatures at bottom to top increasing. And what's this yellow phase up here? This is super critical. And for those of you thermodynamics enthusiasts, you'll like this. You can see the phase change over the classic phase diagram. This is a classic phase diagram for a mixture, right? You can see the bubble form on the left here. As we go even hotter, the bubble grows, that red bubble grows, and then it's all gas, right? So that's the edge. We went from here to here. But up here, what happens? Right from that temperature to that temperature, 0.1 Celsius. Boom. Supercritical fluid at that high pressure. So anyway, lots of fun for mechanical and chemical engineers. But the great thing is, if you were to, if you like, say that's a data point right here, if you were to call up a services company and say, hey, I need this at this pressure and this temperature, I need to know the phase volume of this mixture, they'd say, sure, send us a sample, $5,000, right? So it's possible to get a lot of data. Again, information's a product. We get a lot of phase data here from a small chip. We, of course, validated this with various models and test fluids. And this is an example of, you can see this thing pressurizing. So this is this, we call it the piston test fluid. And here's the fluid under test. When it gets up to pressure, you'll see the two phases drop out. And there we go. And then if we cruise over to the right, we go to higher temperatures. We can say we have more gas there. And then we can move around, etc. So we can, in a way that was never possible before, we can move around the phase diagram. If that example was a bit of a Ferrari, or maybe it was a British race car, very fussy, very cool, very high tech. This is the opposite, this example. This is a single channel, right? And you fill it with your sample here, in this case, an oil, and then you bring in CO2. There's lots of interest for CO2 and oil interaction, CO2 storage and oil reservoirs. and CO2 use in enhanced oil recovery. So this is a super simple system where we can bring in high pressure CO2, and you can see here, over 7.3 megapascals. Um, we get very different behavior in terms of from oil swelling to oil light fractions in the oil moving into the CO2 phase. So there's just a ton of data here, and so we use this to extract more or less. I call it Ali and Atena, who are the lead authors. Measure everything. There's extraction pressure, minimum miscibility pressure, contact angle, right, as a function of temperature and pressure. Diffusivity, minimum miscibility pressure. They just pulled a ton of data out of this thing. So this has been a very useful test, and a different example than the British sports car I showed earlier that was really fancy. This is more of a Ford tractor. Great. So this we also apply this in other ways to look at interactions between CO2 and how CO2 might be stored. Here, this is a nanoparticle stabilized foam example, and nanoparticle stabilized foams are much more stable than just surfactant stable foams. For instance, here after 10 days, we've got lots of bubble bath, in this case CO2 bubbles, whereas surfactant very little. So that works well underground as well. So this is enhanced oil recovery is really the major industrial use for CO2 right now. I'm hoping that there's more and more use for CO2, so we can address our climate challenges. But right now, the big one is enhanced oil recovery and some CO2 storage associated with that. So where does that happen? That happens in places that have medium heavy oil. Light oil, like your Saudi Arabia, they don't need it. Look at this CO2. It helps a bit, but who cares? Because water was pretty good in terms of moving oil. Heavy oil, you think about Venezuela, think about Alberta. It works a bit, not great, but it's in these medium heavy reservoirs where you get this combination of CO2 and storage and oil recovery. It's an interesting pairing. If there's questions on this, I'm happy to talk about it because some people find this confusing. In some ways, it seems like a climate technology because you're putting CO2 underground, you're storing it. In some ways, it doesn't because you're producing oil. It's a complicated combination, and I'm happy to chat about it because it's interesting. As we go, as our journey moved, and this is getting to about 5 years ago, we started to look at smaller scales and towards nanofluidics for energy applications. And these setups are complicated and terrible to run because the scales are just so small. So an example, I'll skip ahead here. An example is you can't even see these fluids in these channels, right? So you put a fluid in these channels here, and you look at it with a microscope, and there's liquid on this half and gas on this half. But you're going to have to believe me, because you can't see it, right? There's nothing visible there, and that's because this is such a small scale channel. But if we put some photonic layer on here, some silicon nitride, we actually make a refractometer, which is really cool. And you actually, from a traditional microscope, you see these two different phases. You see bright, what is that, fuchsia, and light pink here. And the exciting thing is not the flamboyant color scheme, but the fact that you can now see liquid phases at nanoscale. And of course, this is important for a bunch of applications. And in the energy industry, right? What has changed global energy profoundly over the last 20 years has been hydraulic fracturing. It's very what's the word? Contentious, right? And its value has been disputed greatly. One thing as a mechanical engineer, I know it's a complex process that's important, globally important, and it needs to be understood both from environmental hazard perspective and from an economics perspective. So we took we realized we needed to understand this better, and fluid flow in these super small scales is so challenging. So we developed these systems where we got microscale here and nanoscale here, and I'll take you through these fairly quickly, but again, looking at the phase diagram, seeing what's liquid where, what's gas where, what temperatures and pressures. Here we see a deviation as we get smaller channels. Look at this, 8 nanometers. You know, then we get this shift in the dew point, right? Early dew point, early condensation, and then if we look at the full phase diagram here, we get bubble point and dew point, and you can see the microchannel reporting right on time here. Micro scale stuff does a good job of of phase behavior. But the nano stuff, not so much, right? So you get deep down here into the phase diagram before the nano stuff, even below the dew point before the nano scale stuff starts to evaporate. So a complex combination, fascinating combination of phase properties and length scales. And here you see some nanoscale phase behavior as well. Great. And we took this to a commercial scale, looking at, well, how can this inform energy operators? How can it inform people who actually have energy operations in this area? And we developed this. This is a little bit like the Ferrari I mentioned earlier, kind of fancy academic work. This had 31,000 pores, 31,000 pores. I said with little wee 5 nanometer throats joining them. So it's a very complex, very stubborn mechanical system. With very interesting phase behavior. So I won't take you through that, but this looks like a computer generated image. It's not. It's a microscope image. Or sorry, it's collected from microscope data and then coded in time based on when the phase change happened, and the evaporations was from bottom to top here. Very rich system in terms of data and in terms of physical complexity, which reflects the challenge that is underground. Great, so I won't take you through all the details here, but some very interesting dependencies on when you have this combination of extreme mixed geometries and multi-component fluids, right? Here we have a C1, C3, C5 mixture. Very interesting physics here that these tools help us understand. As I mentioned, that's a bit of a fancy car. That's not very well suited to industry, but a small scale version of that was developed by my student Genji Song, and this is very applicable to industry. So you could assess, well, how well do different fluids behave, and one real point of hope for me anyway is that CO2 injection will start to be used in nanoscale reservoirs. Because you got an opportunity to store that CO2 there. And 2, it just works really, really well, far better than nitrogen at these scales, as an example. So CO2 is, we think of it as an emission, but it's also a very useful fluid. And I think part of the challenge, or the opportunity in dealing with the CO2 challenge is finding use cases, and this is one. Excuse me. Yeah, if you're interested in nanoscale stuff, there's not just those applications, those are the energy industry applications, but there's all sorts of nanoporous natural systems, engineered nanostructures. We wrote this review paper together with the Doan group at Boston University on the interesting physics at this scale. I think coming back to the industrial offering here, one last step for us was to make these chips cheaper, right? So don't forget, we're trying to get data from these things. That's the product. But when they're relatively large, they cost a lot of money to make. So we realized we could shrink these down to be about 1 centimeter long. And if we developed a special pore, a special manifold. So this was really the last step to getting industrial microfluidics. So microfluidics that can take high temperatures, high pressures, industrial microfluidics into the marketplace. So that was our U of T startup, and I'm part of this company still. I started as CTO, and I apologize. On the main slide, I think I still had CTO. I've now been demoted to executive energy advisor or something, technology advisor. But it's good to be demoted because the company is growing. They need a full-time CTO, and they've got a great one. Yeah, so I'm still very much involved with these guys, and it's exciting. They do a lot of work in PVT and phase behavior. They will study any fluid that you can send them at any condition. Who has been the big buyers for that to date? It's all been oil and gas companies, but more and more we're starting to hear about interest from companies doing hydrogen and companies looking at CO2 storage. So we're really hoping that this technology is positioned, because this technology can work for any fluid. So we really want to, we think there's a great opportunity to be part of the energy transition as soon as that industry scales. So we're all cheering for it. We're cheering for hydrogen. We're cheering for CO2. And by the way, what kind of challenges might one encounter? Well, transport. The phase properties of transporting CO2 is critical, very important. If there's a little bit of water in there and it drops below critical pressure, you get water dropout, and then you've got acid flowing in your pipeline. Not good. Hydrogen, many examples. So I'm really upbeat about this company, both based on its current business and where it can go in the next few years. We're fortunate for the industry folks in the audience to recognize a bunch of these names. These are some of the biggest companies in the world. The ones above that work with us, there's ones above here are our energy companies, and the ones below are chemical companies, and both of which are interested in testing our services, again, getting the data that we can provide them. And those who have been involved in the startup world will recognize Techstars and Creative Destruction Lab, two incubators that were very helpful for us in scaling. Now, back in my lab, with that technology really moved to industry, I don't want to compete with my own startup company. So my lab started to look at, well, what can we do in other industries in the energy sector? What can we do using our tools? And one very productive partnership has been with Ever Technologies. These guys have a very cool renewable tech, and it's this closed loop geothermal system. So the idea, and you can see this borrows a lot from oil and gas, right? Directional drilling. These clever guys at Ever Technologies said, hey, listen, we can use directional drilling that's been developed now, and we can use it to come down from one side and then come down from another side and meet it. So it's like a moonshot in terms of accurate drilling, but it's possible. They've demonstrated. It's fascinating. For anyone who's been involved in drilling technology, hats off to you. It is so incredibly complicated, but the technology is developed so well that you can do geothermal energy like this. You can have a closed loop radiator, essentially. And when you do that, you can have a special working fluid. In conventional geothermal energy, you push your fluid down in the ground, you hope it comes back hot, but you can't have any valuable fluid there. But closed loop, you can. So we're looking at, can you use, paraffins? Can you use particles that are like phase change particles, and you can draw more energy out of that reservoir and more geothermal, more renewable heat for electricity, renewable electricity, or for just renewable heat for industrial processes. So this was a microfluidic chip, and you can see the general idea was, again, to mimic that industrial environment. You got this fancy material we've drummed up, and now we're testing it. So in through the cold side, then hot, then cold, then hot. This is sort of equivalent to what you would get if you were cycling through this, excuse me, if you were cycling through this geothermal well. So we get the temperatures right, the pressures right, even the shear stresses right. We get a lot of data from these small scale systems that can help us determine if this is a possible technology for a geothermal well. Again, renewable heat, renewable electricity. And then on CO2 sequestration, I mentioned it a couple times today, but here's an example where these types of technologies can inform on CO2 injection into where it's just intended to be stored permanently. No recovery of oil, just CO2 sequestration. There's lots of interest in this area now, especially with companies like Microsoft and Stripe and Shopify, Canadian company, funding CO2 sequestration. So they're funding CO2 out of the atmosphere and into permanent storage, and the best permanent storage tends to be saline aquifers. But there's some challenges down there, as you might expect, right? This is a new application. When you start jamming CO2 into a saline aquifer, what happens? Well, you get some of the water evaporates into the CO2 phase, and some of the CO2, or rather, the CO2 moves into the aqueous phase, and you get acidification. And we can use a microfluidic environment like this to assess that. Here are some channels, some microfluidic channels. These are about the size of a hair. And we can we can inject CO2 and we can see where it goes. And you can see this is getting darker here, right? So this is still liquid phase, but it's getting darker. That's CO2 moving into this solution. This is a fluorescent dye. And it's acidifying. So the dye fluorescence is pH sensitive. So it's kind of cool. We can see CO2 in the gas phase, and you can see its effect in the liquid phase. And you can plot this out, of course, and then ultimately you can see salt formation in these systems. So you can really capture a lot of the physics that's happening, and that's so topical right now, as I mentioned, with these companies looking to store CO2. You can capture a lot of that physics using microfluidics, and that can help you inform your CO2 storage applications. Great. What am I doing for time here? 10 minutes left. I'm going to skip this guy because I want to talk about electrocatalysis and the latest work that we've done. Very briefly, in bioenergy, we did a bunch of work, and one example of that is looking at how cells respond to light and gradients in nutrients, and the key outcome was that we could produce some really cool plots that told us where, for instance, cells grow really well at particular conditions, right? You remember the phase diagram, temperature and pressure. Well, here we're talking about a phase diagram of ammonium concentration and irradiance, right? So a very particular condition identified here where it grows really well. And then we did some other work looking at modified reactors and lots of them and high throughput. I won't take you through all the details here. Okay, so if all those applications were where information was the product, right? We were trying to find out how, in that last case, how well we can grow bioenergy. Or earlier we were thinking about how well we can inject CO2 and store it, or how well we can have oil interact with CO2 to achieve recovery and CO2 storage. All those cases. All those cases, microfluidics worked great. All the tools look the same, right? They're always a little chip, and it worked pretty well, or at least by the time it got to you here, it worked well. And but when you want to actually make a fluid, right? When you want to actually produce, say, convert CO2 into something, you're not trying to get data from the process. You're trying to get fluid. You're trying to make gasoline or something, or ethylene, propylene, propanol. Then, if you try to do it with microfluidics, things go very bad. And I can tell you, I'll give you an example of the world's most expensive biodiesel that I made, if there's interest in that. I think it was $10 billion a liter, I estimated the cost. So, too much. But does that mean microscale people like me can't contribute to large-scale energy systems? We can't. We can only do it through things that we've discussed already today. Over the last few years, I think we've proved that that's not the case. We can make contributions, and one way that we've been working in is CO2 conversion. So if you think about, there's lots of available of CO2 that's going to be available for many years. Lots of emissions. But the biggest change in the energy system over the last few years is a reduction in the cost of solar energy. It's radically reduced. And the other thing is that there will be long-term demand for hydrocarbons. We know that fuels for sure, but chemicals, plastics, ethylene, these are the core material flows of modernity. So how can we combine these? How can we take electricity and turn CO2 into what there's going to be demand for instead of digging up fossil fuels? So make synthetic products from CO2 using electricity. So our approach is this one. So we've got sources of CO2, maybe industrial power emissions, or from burning of fuels and households in CO2 emissions into the air. If you bring that CO2 from those two sources into the electrolyzer, and then you can produce some fuel, or increasingly we look at chemical feedstocks, things that we can't live without. And we do all that with renewable energy and water and CO2. And the pathway for us over the last 6 years has been has been starting small. So this was our first work in partnership with the Ted Sargent's group at University of Toronto. And here we had some nanocatalysts, super small, that were making a small product CO. And then you can see the progression over the next 5 years was 6 years was to larger scale systems and larger scale molecules, multi-carbon products, and larger scale systems. You know, these are electrodes and then systems, and then eventually the world's largest pilot plant that we built as part of the X Prize competition in 2020. So a couple quick examples here. The on the input side, one wants excuse me, low cost CO2, low purity, ubiquitous sources, and then of course in the cell you want it to be productive, and in the output you want it to be valuable and pure. So this is every chemical engineer's dream, of course, something cheap through something efficient to something pure and valuable. That's the goal. But the reality is quite different, and we actually can't use flue gases in current systems like this. So we looked at, well, can we at least start to react one a sort of a entry-level flue gas with some oxygen in it, not pure CO2. So I won't take you through all the details here, but it's motivated by the idea of consuming flue gas directly, avoiding the cost of CO2 capture, which is substantial. And here, what I want to show you is the microchannels that made it happen. Now, they don't look like microfluidic chips like I showed you earlier. When you were talking about bulk fluid production, you can't use those things. But you can use micro nanoscale phenomena. Look at this. So these small scale channels here are hydrophilic, so they fill with water and they stay filled with water. They keep the catalyst surface wet, and as a result, they keep oxygen, they slow oxygen compared to CO2 because of CO2's higher solubility. And as a result, we're able to basically react streams and reject that oxygen. One small step towards a flue gas reactor. In the cell, another example of microfluidics within large-scale systems, this is a big challenge in these systems is CO2 crossover. So you want the CO2 on the cathode, you want to convert it into products like ethylene, ethanol, propanol. But it doesn't always do that. Sometimes it goes into carbonate, and that carbonate crosses over, and it's a huge problem for the field. This technology, we put some microchannels in there. We said, well, we need to split this membrane here, and we need to add some channels so we can allow that CO2 back and recycle it. So in previous cells, it's like a fuel cell almost, and there's a simple membrane there. And here the innovation was putting channels inside that membrane over a relatively large area. So again, microchannel tech, but over a large area and inside a large system. So this ended up working really great. So we ended up getting, you know, very very pure CO2 circulated right back into a reactant. We didn't have to recapture it, and very little cross to the anode. So this is an example of maintaining your reactant, which is a good mechanical engineering, chemical engineering goal. Yeah, here's another diagram of that of those channels and that channel pattern, getting the CO2 out before it crosses over. Again, to me, this is my favorite example of microchannels being useful in a large-scale energy system, right? Not in a chip per se; those were more for data, but in a system that needs micro-scale transport. Great. So wrapping up, you know, we're motivated by energy and environment, and I make the point as a fluids mechanical engineer that these really are the fluids challenge of our age. I'm passionate that all solutions must scale to the gigaton level, right? We have to have everything we talked about today. Not all of it is gonna change the world. Some of them will work and some of them won't. But we did them all with a motivation that it could be scaled, that the outcomes could be scaled and could either inform an industry happening at large scale, right? Help them operate more efficiently, smarter, or in a second chapter, how we could use microscale transport cleverly to make big reactors work better. CO2 utilization and CO2 conversion were the overall themes in those 1-2 chapters. Great. And I'd like to acknowledge funders for this work. There's been many over the years, and my research group, who of course do all the work, and also collaborators. I mentioned Ted Sargent's group and others along the way in my presentation. It really is a multi-group effort. And lastly, thank you for your attention and for the opportunity to speak today. And I hope we can have a discussion.
Thank you very much, David. It was very interesting. Kyoto is saying that this is a very interesting topic and talk. I'm very intrigued about the shear forces, wall flow losses, and boundary layers at micro and nano ducts. Please, could you comment about these losses?
Well, there's a lot. There's a lot there. By the shear forces, wall forces, boundary losses. Yeah. So right. So I think I get your question, and it's a good one. And you're trying to convert large scale fluid mechanics. Right? That is the bulk of our profession focuses on, to micro scale. And I guess a few things. What I would say to guide you down in terms of scales. One thing is everything gets laminar, right? One can work out the Reynolds number of a channel with water in it at at 100 microns across, and you have to have a screaming high velocity to get it to be turbulent. So even fluids that we associate with turbulent flow are laminar. That's the first thing I would say. So get used to everything being laminar. And I tell my students it's hard to picture water. Water is so on a scale of us humans, it's so low viscosity. But you have to picture that like honey, very, very, so the effective viscosity is high. Of course, the viscosity doesn't change, but the nature of the flow at small scales, when one has to picture a much higher viscosity. So in terms of boundary layers, right, the channels are, if you calculate, you go back to that undergrad textbook, graduate textbook, and you calculate the development length, right, in a microchannel, you'll find it's it's like right up at the entrance of the channel, right? So the boundary layers grow in instantly. So there's not that classical, boundary layers growing into the channel. It's essentially, just picture an incredibly viscous fluid squishing through these channels. That's probably the right way to think about it. It's all laminar and almost all of it fully developed. And so just last point on that, when you think about fluid mechanics people like me, who, whatever, 50 years ago, 30 years ago, would have made their life studying turbulence or studying boundary layers, more so in large scale flows, many still do. When you move to small scale flows and you don't have any of that complexity, what do you study? Like, it's all laminar. In some ways, those profs from 30 years ago would say, David, the stuff you're doing here is too easy, right? So from a fluid mechanics perspective, in some ways, it is far more straightforward than the challenge of at larger scales. Where I will say, where we do introduce complexity is adding in chemistry and surface effects. So surface charge effects, and also in capillarity, right? Because those forces grow, they become very, very strong as you reduce in scale. So capillary forces become very, very strong and challenging and interesting. Yeah, and just last thing on that, when I did my PhD kind of in the early 2000s, capillary forces were known to be challenging, but they were just thought to be a nuisance. So you just got those things out of your system as soon as you could and worked with all liquid or all gas. But of course, what we were missing there was a great opportunity, and many groups around the world have made their careers, have made their fortunes on using those strong capillary pressures at small scales to, as small reactors, or to do interesting biology stuff. Lots of applications.
Well, thank you very much. And I have a question. What do you think we can do to speed up this process of um, um, introducing this solution to the industries and make it more general? And also, I have another question. How much do you use the numerical simulations? And do you think if there was a very good numerical platform for specifically microfluidics, would that help to speed this process up? Or
Yeah, great questions. The first one, how do we move technologies to industry? Not just microfluidics things that we do, but general. I think your question was general in terms of the energy transition. It's tough. It's tough, right? I think there's a lot of work that needs to be done at the regulatory level to speed things up. Especially when it comes to big projects, right? Here we're talking about small scale devices and technologies. Those can, as soon as you get money, those can scale out to industry reasonably well. But big energy projects, the type that we need offshore UK, wind and among other sources, those are hard to get approvals for. It's too slow. So there's some policy issues there. I don't know how we're going to solve those, but we need to figure it out. One very happy example of where we did figure that out is recent. I believe it's Germany that built a LNG plant in like 17 minutes or something. Well, I joke, but it was very rapid. I mean, it was a year or something. It was just incredibly fast compared to how long those projects used to take. You take 10 years to just get approval to do it, right? And then you got another 10 years. Anyway, so when we want to act quickly, we can, but we just need to align on that. So there's a policy piece, there's a public piece, and then engineers like yourselves are ready to do it, I think. Your second question was on simulation, and yeah, there's a huge role for simulation. I didn't show much here, but that's not because it's not valuable. It's more just because I'm an experiment. So as you specialize in one's PhD and then in one's academic life, you tend to narrow a bit. And within my, I started a mechanical engineer of all stripes. Then I became a fluids guy, not so much solids and mechanics. And then inside fluids, I became an experimentalist. And the rest is kind of history. So that's my worldview. But we use a lot of simulation to help plan. Help reduce iteration in the lab, to be smarter about our experimental systems. And then last thing on this, we're starting to use more and more computation to plan experiments. So I didn't show examples of this today, but we've got some examples where we're say designing a fluid for, I gave the geothermal example, but we could think about electric vehicle batteries or other types of fluids that one needs now. And you've got a system that's flushing them through your chip that's doing the measurement. Maybe it's measuring viscosity or heat capacity. And you're looking for a very particular figure of merit. Well, machine learning is great for that, right? So you can once you have an automatable system, then you can take the operator out of that and put a machine learning loop on it, and have it predict the next best experiment. And it's very simple. I know machine learning is sort of all over the place these days, and there's lots of talk about full. They can talk to, and some argue is conscious. I'm not talking about that level of artificial intelligence. I'm talking about very basic, very user-friendly machine learning, like Bayesian optimization. It's really not that challenging to implement, and it's very effective. So you just have a machine chewing away there, trying to find an optimum that you've defined, and that use for computation or computational automation, I find very useful.
thank you very much. I see no other questions. One more. You mentioned the use of microfoams to store CO2. Would it be possible to use similar technologies to store hydrogen?
Yeah, it's a good question. I think so. One thing with hydrogen storage, we're still sorting that out, aren't we? But yeah, I guess the answer is maybe. Maybe it would be worth having a look at. Hydrogen is so slippery. I mean, it's just the world's smallest molecule, right? Or close to it. So it's really hard to contain it. My instinct would be to just use the same thing we do with methane, right? Subsurface storage. I'm always amazed how utilities store methane. They get this valuable stuff and they just drive it underground, and then when they need it next winter, they just take it out, and it works with remarkably little loss. Hydrogen, presumably that would be the place to start, but will hydrogen be as well behaved as methane in that case? For sure not. So the question is, how well behaved is it? Can we afford the losses? So good questions. I think we don't know.
Okay, thank you very much. I guess that's it for the questions. Back to you, David.
There we are. Right. That was a very interesting presentation that you gave. I can't say that I followed every small item that you spoke about, but I
Sure.
think I got the gist of what you were saying, which is basically what I wanted to get from it. I was interested in the development of microfluidics for thermal energy generation. You know, I think that is quite a leap through, a leap forward, and hopefully that can become something quite significant in the very near future. So I think that's a very good point. And the other one, of course, I found interesting was the conversion of CO2 using electricity instead of bringing oil and gas from underground.
Right.
And that also is another area that we're making use of the CO2 rather than creating more of it. So I think that's
Exactly.
very good. That's my interpretation of what you said.
Yeah. Well, no,
yeah,
that's good. I'm glad that resonated. Thank you.
yeah. So that was so. Thank you very much for delivering that lecture. I'm sure a lot of the people who attended will have found it very interesting, and you know, there'll be a few questions that they will be asking in the future. So, can I thank you in our usual way? We're not together, so we would normally show an applause. So, if we could really clap for you, and thank
Sure.
you very much indeed. I will send you a little note of thanks from the institution over the next couple of days. And again, thank you very much indeed. So that almost brings us to the end of our lecture session today. Our next lecture will be on the 14th of February, and I'm hoping it's on the subject of wind turbines. We've had a slight problem with the speaker, but I'm hoping we can sort that out. If we can't, we will certainly have another lecture on that day that will be of equal interest. So thank you all for coming along today. Please attend the lecture in February and our future lectures during the year, and enjoy the rest of your evening. Thank you very much. Bye. Okay.
Thank you.
Bye, everyone.
Thank you, David. Thank you, everyone.
Thank you. Yeah.